Okay, we've spent the first part of this particular unit talking about the different types of bonding. We started by talking about metallic bonding, which is how metal atoms hook together to form solids. And what they do is the metal atoms shed their valence electrons. Those valence electrons migrate around all the nuclei, and the attraction of the negative valence electrons to the nuclei hold the piece of metal together. We call that a metallic bond. We talked about how metal and non-metal atoms can form compounds. They actually create positive and negative ions because of the metal's tendency to give up their valence electrons, the non-metal's tendency to gain valence electrons, so positive and negative ions are created. Positive and negative ions are oppositely charged. They naturally attract and they stick together, and we call that attraction an ionic bond. We spend most of our time talking about what happens when non-metal atoms approach each other. And because they both have a tendency to gain electrons, nobody wants to give it up, they wind up sharing electrons, and they form the type of bonding called covalent bonding. And we introduced a way to represent covalent bonding by drawing what are called Lewis structures, where we draw dashes representing shared pairs of electrons. And we've recognized just from experimental data that if we can achieve a Lewis structure that has a noble gas configuration, that pretty much matches the real bonding we find in the molecule experimentally. So trying to make octet configurations and minimizing formal charge gives us accurate Lewis representations of the bonding. Now, how do atoms actually share their electrons? This was the theory put forward by Linus Pauling called Valence Bond Theory. And that means that two atoms that are nonmetals will share electrons if you take an orbital on one atom and an orbital on another atom, and you overlap them and merge them together. The electrons will go into that newly created merged orbital, which is called a molecular orbital, and the electrons in that molecular orbital attract the two nuclei, and the atoms are bonded together. That was called valence bond theory. If you've been reading the textbook doesn't say valence bond theory. The textbook says localized bond model. They're really the same thing. It's just most textbooks use the term valence bond theory instead, but our textbook uses a localized electron model is actually what it's called. Well, this valence bond theory has been really good to us so far. We've been able to predict whether atoms are bonded together with single bonds, double bonds, or triple bonds. We've predicted whether molecules have this property of resonance. We've learned how to predict the shapes of molecules. We've learned how to predict the polarity of molecules. But there's a few things that valence bond theory cannot predict that we haven't talked about yet. Valence bond theory cannot predict whether molecules are magnetic or not. You probably don't know this, although there's a picture of this in the textbook. If you take gaseous oxygen and cool it down to negative 180 degrees, it will liquefy. And you can have liquid oxygen, very similar to liquid nitrogen, which you've probably seen before. If you pour liquid oxygen over a magnet, it sticks to it. Oxygen is a magnetic substance. Most of us wouldn't have thought about that. How would we know it's magnetic? The Lewis structure for a diatomic oxygen molecule doesn't tell us it's magnetic. If you think about what is magnetic out there in the real world, things like iron, we make magnets out of. Things that have unpaired electrons are what are magnetic. And an iron atom has unpaired electrons in its d sublevel. It can actually become magnetic. Why would diatomic oxygen be magnetic? If you draw the Lewis structure for a diatomic oxygen molecule, you have a double bond and a bunch of lone pairs. All the electrons seem to be paired up. So there must be something wrong with our Lewis representation of diatomic oxygen because it's not predicting this. Another thing that valence bond theory can't predict is the electron arrangement of molecules that have an odd number of electrons. I don't know if you've been keeping track, but every molecule that you've drawn a Lewis structure for in the past 2 weeks always has an even number of electrons. And you're going to think about that. You need to have an even number of electrons if you're going to wind up getting octets around all the atoms. You can't get octets for all the atoms if you have 17 electrons in a molecule. The textbook went through an example of a molecule that had an odd number of electrons. And if you read that, it said, I don't really know what's happening. Some atom's going to get 8 in its outer shell and some atoms are going to get 7, but I don't know really what's happening in that molecule. It doesn't seem like it should exist. It's not allowing all the atoms to achieve a noble gas configuration. So that's a problem. We can say with valence bond theory and Lewis structures that, oh, that molecule possesses resonance. In this structure, the bond between the first two atoms is a double bond. In the other structure, that bond is a single bond. So in the real molecule, the bond is a 1.5 bond. What does that mean? I don't know. but that's what we say. So unfortunately, we can't really show where the electrons are because I don't know what this fictitious half bond is or third of a bond. So that's a problem as well. And then something else, it actually cannot predict energies of excited states of molecules. We haven't talked a whole lot about this, but if a molecule gets excited and the electron's going to jump up to a higher energy state, it must be going to some new orbital. What orbital is it going in? I don't know. So there are some reasons to understand that valence bond theory really may not be the best theory for how non-metal atoms covalently bond together. It's really good. It explains a whole lot of things and in not too complex a fashion. But in all reality, if we really want to explain covalent bonding, we actually need a more in-depth, more powerful theory. And that's what we're going to do today and on Monday. So in 1932, Robert MULLIKEN and FRIEDRICH HUND decided to propose an enhanced theory for covalent bonding. And it really has to do with what Linus Pauling said about how atoms bond together with his valence bond theory. Pauling said that if you take an orbital in one atom and an orbital in another atom and overlap them together, they will become a molecular orbital. And here's what's important about that. Where are the electrons located when that happens? They're in the region of space between the two nuclei. That was really important conceptually because if the electrons are in that region of space between the two nuclei, they're going to attract the two nuclei. So that holds the atoms together. That's why that's called a covalent bond. Well, MULLIKEN and HUND said, you know what? I don't think Pauling is right about that. I don't think the electrons are going to be stuck in that space between the two nuclei. There's another word for that. They said that I don't think the electrons are stuck in that locale. They're not localized in the space between the two nuclei. So they proposed that molecular orbitals are not localized between pairs of atoms. Molecular orbitals are actually regions of space that can encompass many atoms in a molecule because they're going to be influenced by the nuclei of all the atoms in the molecule. And taking a more holistic approach to bonding that MULLIKEN and HUND are doing gives us what we call today molecular orbital theory. And this is what we're going to work on today and on Monday. So molecular orbital theory essentially is based upon the fact that electrons in molecules will exist in molecular orbitals. Nothing wrong there so far. That's really exactly what Pauling said. Electrons in molecules exist in molecular orbitals. Here we go. But not restricted to the regions of space between pairs of atoms. But they're treated as moving under the influence of all the nuclei in the molecule. So that's going to be the significant difference here. Valence bond theory assumes the electrons are found in specific locales, the regions of space between pairs of atoms. That's why our book calls it the localized electron model. Electrons are localized between pairs of atoms. MULLIKEN and HUND are saying, no, I don't think so. The electrons can be thought of as being influenced by all the atoms, so they're actually located in larger regions of space. Now, how that's going to pan out, we're not going to see until the very end of Monday. But we're going to talk about other aspects of molecular orbital theory, and here's maybe the most important one for today and for our next lecture. If you remember back at the beginning of the semester, the first day, we talked about something that Antoine Lavoisier said about the mass of a chemical reaction. If you start with 5 grams of reactants, you're going to end with 5 grams of products. That was the law of conservation of mass. Mass is conserved in chemical reactions. MULLIKEN and HUND said, when you bond atoms together, the number of orbitals you start with on the original atoms has to equal the number of orbitals you get in the newly created molecule. They said orbitals have to be conserved. So an important part of molecular orbital theory, this will be the most important part today, is that the number of valence molecular orbitals you get in your molecule, and I'll use MO to stand for valence molecular orbitals, must equal the number of valence atomic orbitals from the atoms that you start with. The number of valence molecular orbitals in a molecule must equal the number of valence atomic orbitals from the atoms that make it up. So we're going to use this. Before we do, let me do a little bit of refresher on atomic orbitals. Make sure we're clear on what different atomic orbitals look like. And let me introduce something to you about atomic orbitals that we've never mentioned in class before, but you may have seen it if you've been looking at orbitals in our chapter online, and try to explain something about them for you, okay? So I'm going to look at, let's say, 3 different types of orbitals, because most of the bonding and stuff we do is going to be involved in s orbitals, p orbitals, and d orbitals. We don't do anything with f's too often. So if I ask you to draw an s orbital, you would probably draw a sphere, because you know s orbitals are spherical. If I ask you to draw a p orbital, you need to know it's 2 lobes. It's a dumbbell-shaped orbital, okay? A d orbital is a 4-leaf clover-shaped orbital. So generally speak, an s orbital is a sphere, a p orbital is 2 lobes, looks like a dumbbell, and a d orbital is a 4-leaf clover shape. So if I make a simplified picture, I can sort of draw 4 spheres like this, and that would sort of be representing a d orbital. Where do these pictures come from? Do you remember? How do we know this is what s, p, and d orbitals look like? That's a fine question, isn't it? When we talked about Schrödinger writing a wave equation for electrons in a hydrogen atom, his equation had many, many solutions. Every single solution was considered something called a wave function, abbreviated by the Greek letter psi, which looks like a pitchfork. If you went from San Clemente High School, you have it drawn on the side of your school. So that wave function, if you graph it, can actually give you these different orbitals. Although actually you don't really graph the wave function itself, you actually square the wave function and then you graph that. And if you square the wave function, you graph it, the picture you get will be a highly probable region of space where an electron can be found in that particular orbital. So these pictures up here that I'm showing you are graphs of wave functions that come from the Schrödinger equation that are squared. And so these graphs give you the probability distribution of the electron in the orbital. So whenever you get a wave function for an s orbital, and then you square it and you graph it, it always looks like this. Now it's the wave function from the first energy level, it's small. If it's the wave function from the second energy level, it's bigger. Third energy level, even bigger. But the wave functions for s orbitals, when you square them and graph them, always come out a picture like that. If you have the wave function for a p orbital and you square it, the graph always turns out to have a high probable region at the top of the nucleus and a highly probable region at the bottom of the nucleus. It's always 2 lobes. If you graph the wave function squared for a d orbital, you always get 4 regions of high probability. 1 quadrant, 2 quadrants, 3 quadrants, 4 quadrants, okay? So these are graphs of the square of the wave function of each of these different types of orbitals that came from the Schrödinger equation. Now, here's something, nobody's asked me about this, so maybe you've never seen it before, but in a lot of books, our book does it to some extent, and online, you'll see orbitals drawn and they're going to have little pluses and minuses in them. You ever seen that before? Some people go, oh, maybe this means that the electron is negative. Then what does this mean? The electron's positive? That doesn't exist. Well, maybe this means the nucleus is right there. Well, then what's this? The nucleus is negative? I don't know. Those positives and negatives you see in the different lobes of different orbitals, nothing to do with the nucleus, nothing to do with the charge of an electron. Electron is always negative. It has to do with the wave function psi. Because remember, these are graphs of psi squared. So what significance is, that means psi could either be positive or negative, because when you square it, you're always going to get a positive number. So when you see those little signs in there, okay, those are actually the signs of the wave function psi, because they can be positive or negative numbers. So if you see a little plus sign in here, that just means the psi value that you squared happened to be positive. If you look at a p orbital, you'll notice that one lobe will always have one wave function sign and the other will have an opposite wave function sign. That's what differentiates the 2 lobes. It's like if you were going to draw a wave, you would draw a crest and then a trough. A crest has a positive amplitude. A trough has a negative amplitude. That's kind of what's happening here. The wave function of this part has a positive amplitude. The wave function here has a negative amplitude, but it's not making a whole, right? Because when you square it, they both become positive numbers, so you wind up having 2 highly probable regions of space to find the electron if it's in a p orbital. But the original wave function happened to be negative. And so an interesting thing about wave phenomenon is if you have different lobes, then there are going to be different lobes because this is where the wave function sign changes, positive to negative to positive to negative. So when you look at these pictures, you'll always notice that different lobes in an orbital have different signs. And as you go from one lobe to the next nearest lobe, that's when a wave function sign changes. So if you ever see those in orbitals, that's what that means. And that's going to be really important now as we apply molecular orbital theory. Okay, so what I want to do is I want to look at the simplest molecule of all, a diatomic hydrogen molecule, and see if we can explain the bonding in a little bit more complex theory than either just straight Lewis structures or valence bond theory. In a Lewis structure, you go H-H, single bond. With valence bond theory, you say, oh, I know what that bond is. It's a 1s orbital on the first hydrogen combining with a 1s orbital on the second. And so the bond in the hydrogen molecule is called sigma 1s plus 1s. So that's explaining the bonding with Lewis theory or valence bond theory. Let's do it with molecular orbital theory. So with molecular orbital theory, an important concept is however many atomic orbitals you're starting with, that's going to tell you how many molecular orbitals you get at the end. Now, each hydrogen atom has a single valence atomic orbital, the 1s. So if there's two hydrogens, there's a 1s from the first atom, there's a 1s from the second. You're starting with two atomic orbitals. That means when you form the molecule, you're going to have two molecular orbitals. So just restating, two hydrogen atoms have one 1s valence atomic orbital each. So therefore, you're starting with two valence atomic orbitals altogether. So if you're starting with two valence atomic orbitals, you're going to end with two valence molecular orbitals. So the H2 molecule must have two molecular orbitals in it. We're going to see where those come from. Because if you think about valence bond theory, when you say the bond in a hydrogen molecule is a sigma 1s plus 1s, that's one orbital. Where's the other one? I don't see it. Valence bond theory doesn't even talk about it. But MULLIKEN and HUND said it has to be there. You have to conserve the number of orbitals. Two orbitals, which could hold 4 electrons, can't just merge into one orbital that can only hold 2. Where would the other electrons go? That actually doesn't make any sense. So here's where the two orbitals come from. Let's take a pair of hydrogen atoms. On the left is the 1s atomic orbital on the first hydrogen. On the right is the 1s atomic orbital on the second hydrogen. If these just merged together like in valence bond theory, we would create one molecular orbital and that would bond the atoms together and we would be done. But MULLIKEN and HUND said, no, we need to make two molecular orbitals. How can we make two molecular orbitals? They said it all depends upon what the wave function signs are. If the wave function signs are the same for the two different 1s orbitals, let's say they're both positive, but it would be the same if they're both negative. When they overlap with each other, that's like overlapping two waves in the ocean because waves have positive amplitude. And if you overlap two waves, any place they overlap, the wave gets bigger. You increase the amplitude. So if the wave function signs are the same and these two orbitals overlap each other, then the region of space where they overlap, ooh, can you see that right here? This has double probability. You have a really high probability of finding the electron in this little football-shaped region right here, okay? So this molecular orbital would be the result of adding the two atomic orbitals together. Addition means they have the same wave function sign. I did both positive, but both negative would mean the same. So we would indicate that as 1s plus 1s, okay? Now, where would the other molecular orbital come from? Can you see where I'm going? What if you take the two 1s's and you add them together, but this time they have different wave function signs? If I push them together, what's going to happen when they overlap? Well, positive wave function sign is like a wave in the ocean, and a negative wave function sign is like a trough. And what happens when a wave and a trough overlap? They cancel out. Does that make sense? Yeah. So when you push them together, anytime they overlap, they're going to cancel out any electron probability. Watch this. You'll like this a lot. Oh, canceled out where they overlapped. And you wind up getting a different kind of orbital. This is one that doesn't have a huge amount of electron probability in the middle. It has no electron probability. The yellow is where the electron can be found. This is deep yellow, so that's really highly probable. Here, there's nothing here. You've got probability left and right, but in the middle of the two nuclei, there's like almost nothing. This MO is the result of the subtraction of the two atomic orbitals because it just means we're combining the positive wave function sign with the negative wave function sign. So MULLIKEN and HUND first proposed, you've heard of HUND before, right? HUND's rule, there you go, this is him. You've determined that two orbitals can overlap in two different ways by adding wave function signs or subtracting wave function signs. Therefore, they create two molecular orbitals from the original two atomic orbitals. So of these two that we've just created, the top one I'll call MO1, the bottom one I'll call MO2, okay? Let's see if we can describe them. When we talk about molecular orbitals, we like to describe their symmetry. So we've seen with bonds, there are sigma bonds and there are pi bonds. It all has to do with the symmetry around the internuclear axis. So if I draw an internuclear axis that connects the nuclei of the two bonding hydrogens, and imagine this orbital just slowly rotating around like it's on a barbecue or something, spinning around on a rotisserie, it would always look the same. It's like a football. Spin that football around, always looks the same. That means this is a sigma molecular orbital. The same thing's true for the other orbital, MO2 here. It's a little bit harder to tell, but actually this is a perfectly symmetrical arrangement. If you rotate it around, it's going to look exactly the same as well. So both of these would be considered sigma molecular orbitals because they have perfect symmetry around the internuclear axis. So much like we define bonds in the same way, orbitals exactly identical as well. Sigma molecular orbitals would be any orbital that is completely symmetrical around their internuclear axis. So if I'm going to name each of these orbitals, I'm going to name them with sigma. Okay? Now, there's a significant difference between them. One of these orbitals has a really low energy, and one of these orbitals has a really high energy. Now think about what low energy means. That means attraction. So which one of these orbitals would cause the most attraction? Now think about what's attracting. We have a nucleus here, and a nucleus here, and then the electrons are in the yellow. A nucleus here, and the electrons are in the yellow. Which one of these two orbitals is going to make the most attraction between electrons and the nuclei? What do you think? And let's see, nobody's talking, so somebody's coming with a chat. So Mr. DiFilippo says MO1 is correct, because if you have a lot of a negative charge in the middle here, and the two nuclei are right next to it, that's going to cause a lot of attraction. In fact, that's more attraction than you get just in a regular old hydrogen atom. Where in a hydrogen atom, the electron only gets to attract to one nucleus. Now the electrons are here, they get to attract to two nuclei. So this orbital will be more stable than the original hydrogen 1s atomic orbitals. Anytime that's the case, we call that type of molecular orbital a bonding molecular orbital. So MO1 is a bonding molecular orbital. It's an orbital lower in energy, which means more stable, than the original atomic orbitals. And why is that? Because most of the electron density is right there between the two nuclei, so the nuclei can attract to it. And the more attraction you have, the lower the potential energy of the orbital. So if I want to indicate that in its name, I already know it has sigma symmetry. I put a little superscript B. This is called a sigma bonding orbital. Okay. Now, if you look at the other orbital created, MO2, the two nuclei are located here and here. So those two nuclei now are facing each other, and two positives next to each other are going to repel. So that means this orbital is going to be very unstable, which means it's going to have a high energy. It'll have a higher energy than the original 1s atomic orbitals. Any molecular orbital whose energy is higher than the original atomic orbitals is called an antibonding molecular orbital. So MO2 is an antibonding molecular orbital. It's an orbital higher in energy than the original atomic orbitals because most of the electron density is outside the two nuclei. That makes the two nuclei face each other and repel, and repulsive energy means high energy. So to indicate that MO2 is an antibonding orbital, you could write a sigma with a superscript A, but for some reason they decided not to go with the A for antibonding. They decided to go with an asterisk, which is read as star. You can call this sigma star, or most commonly it's read sigma antibonding. So the two molecular orbitals that are created when two hydrogen atoms bond together are a sigma bonding orbital, which will be low in energy, and a sigma antibonding orbital, which will be high in energy. And I want to now show an energy graph relating the energies of these two orbitals to the original hydrogen 1s atomic orbitals. And of all the skills you're going to learn today concerning molecular orbital theory, this is going to be it. I'm going to want you to be able to draw what's called a molecular orbital energy level diagram. And so we're going to draw the molecular orbital energy level diagram for diatomic hydrogen. Now, you've done energy level diagrams for hydrogen atoms. You had to do that on the first test. What do you do first? You label what you're graphing. If you're graphing energy on the y-axis, you write energy increasing going up so people know what you're graphing. Then for hydrogen, we put different Bohr orbits on here, and you were showing me the energies of the different Bohr orbits. Well, now we're going to do it for a diatomic hydrogen molecule. And usually what we do is we draw the energy of the atomic orbitals of the bonding atoms first, and we draw them on the very left and the very right. So hydrogen has its outer shell, the first energy level, only consists of a single 1s orbital. So I'm going to draw the 1s orbital on my first hydrogen here. And then for the second atom, I'm going to draw the energy of its 1s orbital. And every single hydrogen atom is identical, so the energy of the 1s on the second hydrogen has to be exactly the same as the energy of the 1s on the first. Okay? How many electrons does a hydrogen have in its 1s orbital? Has 1. And so these are the two hydrogen atoms. So as we just said, we're going to assume these two hydrogen atoms are flying around in space, and now they're going to come next to each other and they're going to merge. And when they merge, the 1s and 1s orbitals can combine with the same wave function sign to make one molecular orbital, and they'll combine with opposite wave function signs to make a second molecular orbital. So the first one is going to be the bonding orbital, and it's more stable than these 1s's, and so we're going to draw the orbitals for the molecule in the middle, and the bonding orbital is going to be lower in energy than the two 1s's, so I'm going to draw it down here and show some dotted lines going down to it like that. Okay? That's our bonding orbital. It's called the sigma bonding molecular orbital. Quite often they add one extra term to that because this was a combination of a pair of 1s orbitals. They're going to call that the sigma 1s bonding. Then the two 1s orbitals can combine by subtracting their wave function signs. And if you do that, you create an antibonding orbital, and its energy is going to be much higher. So you draw dotted lines up to that on the very top. Okay? So these are the two orbitals that are created. The bottom one is called the sigma 1s bonding. The higher energy orbital is the antibonding one. Its name is sigma 1s antibonding. And the final step now is to go, let's put the electrons into these molecular orbitals. Because if the hydrogen atoms cease to exist as individual entities, but they merge together into the diatomic molecule, now the 1s orbitals don't exist anymore, and these molecular orbitals exist. So where do electrons go? They do this in atoms and molecules. They always pick the lowest energy orbitals first. So they're both going to go bink into here. Okay? So this diagram is kind of showing you a before and after. Okay? What do the electrons in hydrogen atoms look like before they bond? They look like this. Hydrogen atoms are flying around. Each electron is a 1s orbital. But if the hydrogen atoms bond together, well, these orbitals now merge into two new orbitals, the sigma 1s bonding and the sigma 1s antibonding. So once the atoms are bonded, those cease to exist, and now you have this. And this is how we believe the electrons exist in a diatomic hydrogen molecule, as explained by molecular orbital theory. You need to keep this picture in mind as we now answer a series of questions. So when you drew a Lewis structure for a diatomic hydrogen, you would draw one dash between them. And if I were to ask you, what's the bond order? You would say the bond order is 1 because there's one shared pair of electrons, okay? Well, I want you to be able to calculate bond order from molecular orbital theory, and I don't see any dashes here, so I can't count dashes. So we need a way to calculate bond order. So what did a dash actually mean in Lewis theory? It's a shared pair of electrons. So every pair of electrons that are bonding the atoms together would be considered a bond order of 1. So we're going to calculate the bond order from molecular orbital theory in this fashion. We're going to take all the electrons in bonding orbitals, we'll subtract all the electrons in antibonding orbitals, and then we divide by 2. So let's apply this to diatomic hydrogen. So for the diatomic hydrogen molecule, if you look back at your molecular orbital energy level diagram, how many electrons did hydrogen put into the bonding molecular orbital?
2.
And then how many electrons went into the antibonding orbital?
0.
So you would go 2 minus 0 divided by 2. And that would be the predicted bond order for molecular orbital theory for diatomic hydrogen. That comes out a bond order of 1, which is nice that it exactly agrees with Lewis theory, which actually agrees with experimental data. So nothing really incredibly fancy here, but at least we can calculate the bond order. But here's something that molecular orbital theory can do. Now that you know exactly where the electrons are, you should be able to tell whether something's magnetic or not. So let me give you 2 terms I want you to know the definitions of. A substance is considered paramagnetic if it becomes magnetic in a magnetic field. And something can become magnetic in a magnetic field if and only if it has unpaired electrons. Okay? I'll tell you something that's paramagnetic. Aluminum is paramagnetic. Okay? Now, there are a few things that are called ferromagnetic. That means they're permanent magnets. Iron is an example of something that's a permanent magnet. Okay? Iron has unpaired electrons, and the unpaired electrons are spinning in a certain direction. And then a few of those electrons can affect the electrons near it and cause them to spin exactly the same. And they influence electrons next to them, and they spin exactly the same, et cetera, till you get a really big chunk of iron, and billions of electrons are all spinning in the same direction. And when you take physics, you're going to learn spinning charged particles make a magnetic field. So iron can create a giant region of a crystal that has all these electrons spinning in the same direction. That's called a domain. So it becomes a permanent magnet. Other things with unpaired electrons will actually not completely influence each other, so they all don't spin in the same direction. So aluminum is an example of something that has an unpaired electron, but one aluminum atom doesn't influence the aluminum atoms next to it very strongly, so they don't all start spinning in the same direction, so a chunk of aluminum is not necessarily magnetic. But if you put aluminum next to a true magnet like iron, then the iron magnetism will influence all the aluminum's electrons. They all start spinning in the same direction, and all of a sudden aluminum becomes magnetic because it's in a magnetic field. If you've ever taken a magnet and you've taken a paperclip's made of aluminum, and a paperclip is not magnetic. You should try taking a paperclip and sticking it to other pieces of metal. It won't do that. But if you take a magnet and stick a paperclip onto it, the paperclip will stick onto a magnet. You can take a second paperclip and you can stick it onto the first, and a third and stick it onto the second, because the aluminum is becoming magnetic in the magnetic field of the iron magnet that you have to start with. It's due to its unpaired electrons, okay? Now, if something never becomes magnetic, for example, plastic will never be magnetic. If you try to stick plastic to a magnet, nothing's going to happen. It never will. That's because plastic doesn't have any unpaired electrons. All of its electrons are paired. So something is diamagnetic if it has no unpaired electrons. So if you know where a substance's electrons are, you can look at them and see, are they all paired, or are there some that are unpaired? You can predict whether it's paramagnetic or diamagnetic. So what can you predict about diatomic hydrogen? Would diatomic hydrogen be paramagnetic or diamagnetic?
Diamagnetic.
Because the 2 electrons in the hydrogen molecule are paired together. So therefore hydrogen is diamagnetic. Watch this question. If I asked you, for atoms of hydrogen, are hydrogen atoms paramagnetic or diamagnetic? What would the answer be? Do hydrogen atoms have all their electrons paired up, or do hydrogen atoms have an unpaired electron?
Unpaired electron.
So hydrogen atoms would be paramagnetic. We just can't get a container of hydrogen atoms, because if I put 100 hydrogen atoms into one container, within a tenth of a second, boom, they're going to all bond together and make 50 diatomic molecules. And those molecules would be diamagnetic. But theoretically speaking, if you're out in interstellar space and there's some hydrogen atoms flying around, those would be paramagnetic, but not the molecules. The last thing I want you to be able to do is be able to show me where all the valence electrons are in a particular molecule. We call that its electron configuration. You've done electron configurations for atoms, right? If you're doing sodium, you go 1s2, 2s2, 2p6, 3s1. Well, now I want you to do it for molecules. So just like you do for atoms, you name a sublevel, you make a right superscript for the number of electrons in that sublevel. So for diatomic hydrogen, the only sublevel that has electrons is the sigma 1s bonding. So you go sigma 1s bonding, and then you make a superscript 2, like this, okay? See those parentheses there? Pay careful attention to those parentheses, because if you put those parentheses in the wrong place on the test, I'm going to mark it wrong because you're not clear about what we're talking about right here. What's in the parentheses is the name of the sublevel. In that energy graph, what was that low orbital's name? Sigma 1s bonding. Now, why do we put parentheses and put the 2 outside? Because outside the parentheses, now you're telling how many electrons are in that sublevel. When you say 2p6, 2p is the sublevel, 6 is how many electrons. And we can do the same thing here, but unfortunately, the name of our sublevel already has a superscript in it. It's that b up there. So if you don't put the parentheses, you're writing sigma 1s b squared. It's too confusing. So you put the name of the sublevel in parentheses, then outside of that, the number of electrons. Okay? Lovely. Let's try it again on another diatomic molecule, the second most simple diatomic molecule of all, diatomic helium. So we're going to apply molecular orbital theory to this. We have to think about how many atomic orbitals helium atoms have, because that's going to equal the number of molecular orbitals when we finish with our molecule. Helium's just like hydrogen. Its outer shell is the first energy level. So one helium atom has a 1s orbital. The other helium atom has a 1s orbital. So that's 2. So those 2 atomic orbitals will combine to make 2 molecular orbitals. And we've actually already seen the pictures of what 1s orbitals do when you add them or subtract them. So I'm not going to draw those pictures again, but it's going to look just like for hydrogen. The 2 1s's are going to combine together by adding wave functions to make a sigma 1s bonding. And they're going to combine together by subtracting wave functions to make a sigma 1s antibonding. So the valence AOs of each helium atom are going to combine to form molecular orbitals in the He2 molecule. And those are going to be the exact same orbitals we saw when we did this whole analysis for hydrogen. So it's not going to be any different. So what I want to do is I want to draw a molecular orbital energy level diagram for the diatomic helium. So we're going to do this just like we did for hydrogen several moments ago. An energy level diagram is graphing increasing energy on the y-axis. So you want to make sure you label your y-axis unless you just want to go for a 99 in the next test instead of 100. And then we're going to draw the orbitals for the 2 bonding atoms on the very left and the very right. In this case, the 2 bonding atoms are helium atoms. So I'm going to draw the valence orbital for the first helium atom here, and the valence orbital for the other helium atom way over on the right. And helium atoms have 2 electrons each, so I'll put 2 electrons in the 1s for the first atom and 2 electrons in the 1s for the second. Now, if 1s orbitals merge together, and this is why I don't have to do the whole analysis again, it's always going to be the same, 2 spherical 1s orbitals will merge together and make a sigma 1s bonding, and that's going to be down here. And then if you subtract their wave functions, they're going to merge together to make a sigma 1s antibonding. You need to be able to draw me the shapes of those orbitals. So I asked you, what do those orbitals really look like? I want you to be able to draw those for me, okay? Now, once we know what the orbitals are in the molecule, we've got to put the electrons in there. And here's what's a little bit different from hydrogen. We have 4 electrons altogether. So how are they going to go in those orbitals? Well, they always go in the most stable one first, right? Mr. DiFilippo is going to go to a concert. Is he going to sit in the first row or the last row? He's going to go in the first row. That's the best seat. So the electrons go in the first orbital first. And then once that's filled, the 3rd and 4th electrons have to go up here. Okay? And that would be our molecular orbital energy level diagram for diatomic helium. Now, here's what I want you to calculate. I want you to figure out the bond order for this. Take about 30 seconds and see if you can determine what the bond order is for the diatomic helium. So look back, see how we calculated that. You take the bonding electrons, subtract the antibonding electrons, divide by 2. 2 bonding electrons, 2 antibonding electrons, divided by 2. And I know you may not have a calculator with you, but if you can figure that out, that's actually 0 divided by 2 or 0. Now, that's a really significant number, okay? This means that you have no net bonding force between the two atoms, okay? That means if you have your 4 electrons in the regular old helium atoms, the energy of these electrons is some certain value. If you bond them together, 2 electrons get to be way more stable. That's good. But 2 electrons have to be way more unstable. And the combined energy of these 4 electrons now is exactly the same as the combined energy of these. You haven't had any advantage to bond the atoms together. If the atoms bond together and there's no energy advantage, they will not stay bonded together and they will come apart. Therefore, the helium diatomic molecule does not exist. That's because the bond order turned out to be 0. The bond order has to be a positive number to indicate there are more forces holding the atoms together than repelling them apart. So in molecular orbital theory, we say you could form a diatomic helium molecule, but unfortunately, the repulsive energy of the antibonding electrons exactly cancels out the attractive energy of the bonding electrons, no net force holding them together. If you're doing Lewis theory, you would just go, oh, if I have 2 heliums and I'm trying to bond them, I exceed the duet rule, so it's impossible. Which, you know, you're just making something up and saying it's impossible. But now we can actually see physically where would the electrons be, and energetically, this is not favorable, okay? So let's try this. Let's try a diatomic helium +1 ion. If we ask you, does it exist or not, you're going to have to determine the bond order and see if the bond order comes out 0 or if it doesn't come out 0. That's what's going to determine if it exists or not. So I'm going to give you a couple minutes. I want you to figure out the bond order for this, and you're going to have to do it by drawing a molecular orbital energy level diagram. So essentially you have to do that. And when you draw your molecular orbital energy level diagram, if it seems to indicate that this will exist, I'm going to want you to answer these questions. We'll give you a couple minutes to work on this on your own. I want you to calculate what the bond order is. I want you to tell me its magnetism, and I want you to write its electron configuration notation. So you don't need to give me an answer now. Let's just give you a couple minutes to work on that. And then after a couple minutes, we'll see what everybody has and finish up for today. So in starting your molecular orbital energy level diagram with the 2 helium atoms, here was the important thing you had to recognize. If it's a +1 ion, that means you've lost 1 valence electron. So instead of drawing 2 valence electrons for both helium atoms, you've got to pull 1 electron off of one of them. That's how you get the +1 charge, okay? So now when you complete the molecular orbital energy level diagram, you now have a sigma 1s bonding and a sigma 1s antibonding. Now you have to put 3 electrons into those orbitals, which means the first 2, it doesn't matter which 2, would go into the bonding orbital, and the remaining electron would have to go into the antibonding orbital. Do you think this diatomic ion is going to exist? Yes or no?
Yes.
You have more electrons in the bonding orbital than you do in the antibonding. There's going to be more attractive force than there'll be repulsive force. It should exist. And the way you can verify that mathematically is by calculating the bond order. The bond order is 2 bonding electrons minus 1 antibonding electron divided by 2. That's 1 divided by 2. That equals 1/2. That's bigger than 0. Now, do you think that's a very strong bond?
No.
No, a bond order of 1 was the weakest we learned before, doubles stronger, triples strongest. So if you have a bond order of 1/2, that's like 1/2 a bond. That's pretty weak, but it's still a bond. So that's going to hold those together. That means that should exist. Okay? Would you expect the He2 positive 1 ion to be paramagnetic or diamagnetic? Mr. DiFilippo, what do you think?
Diamagnetic.
This has no unpaired electrons here. Wait, Mr. DiFilippo, what's that up there?
An unpaired.
That means it's going to be paramagnetic. So that electron can start spinning in one direction and create a magnetic field. If all your electrons are paired up, the first electron makes a magnetic field one way, but the paired one makes a magnetic field the other. They cancel each other out. So if you always have an excess electron, that's what's going to make a magnetic field. So this is going to be paramagnetic.
Okay.
And then can you give me the electron configuration notation for this? You have 2 different sublevels that have electrons. This is the sigma 1s bonding. This is the sigma 1s antibonding. So you name sigma 1s bonding in parentheses, and then you tell how many electrons are in it. Then you name sigma 1s antibonding in parentheses, and you tell how many electrons are in it. So sigma 1s bonding 2, sigma 1s antibonding 1.